All right, so we're all on this hunt for the perfect clean fuel, right? And hydrogen, it's always at the top of the list. But it's got this one huge problem. How in the world do you actually store it? Well, today we're going to dive into a potential breakthrough that could change absolutely everything. We're talking about a kind of super sponge for hydrogen.
I mean, think about it. By weight, hydrogen packs almost 3 times the punch of gasoline, and the only thing that comes out the tailpipe is water. So you gotta ask, why aren't we all driving hydrogen cars? The answer is simple and frustrating: storage. Trying to safely and efficiently cram enough hydrogen into a small space like a car's fuel tank is this massive engineering headache that's basically held back the entire hydrogen revolution. So, how are we doing it right now? Well, frankly, our current options are a real trade-off. On one hand, you've got chemical storage, using things like metal hydrides. Yeah, they can hold a lot of hydrogen, but getting it back out, that takes a ton of heat and it's super slow. On the other hand, there's physical storage, giant heavy tanks. These are fast, sure, but they're incredibly inefficient. You either have to use crazy high pressures or cryogenic temperatures. We're talking colder than deep space. So yeah, neither of these is the perfect solution. We need something completely new. So the problem is pretty clear, right? The core challenge is we need a material that can act like a high-capacity, reversible, and super safe sponge for hydrogen.
And this is where it gets exciting. Scientists think they may have found the answer in this really fascinating class of materials. People are calling them crystal sponges.
Okay, say hello to metal organic frameworks, or MOFs for short. The best way to think about these things, they're like microscopic crystalline sponges. They're built from these little metal hubs connected by organic struts, and this creates a structure that is just unbelievably porous. I mean, their internal surface area is so huge that if you took just a pinch of this stuff, like the size of a sugar cube, it could have the surface area of a football field. It's just perfect for trapping gas molecules like hydrogen. Now, out of all the MOFs out there, we're going to zero in on one in particular called QBT. It's made with copper, and it's a fantastic starting point for hydrogen storage. So why this one? Well, its pores are just the perfect size. We're talking zero point 0.6 nanometers, which means multiple hydrogen molecules can kind of snuggle in there and interact with the structure all at once. And here's the really cool part. It has these things called open metal sites, which basically act like tiny little magnets that help grab and hold onto the hydrogen. Okay, so we've got a great base material, a really solid starting point. But you know how scientists are? They're always asking, can we make it even better? And that's exactly what a team at the universities of Exeter and Bath did. They came up with a whole new recipe, one that's greener, way faster, and believe it or not, surprisingly simple. Their big idea was this. What if we could just tweak the atomic recipe of this crystal sponge? What if we could swap out some of those copper atoms for a totally different metal? Could that turn it into an even better hydrogen magnet? And the way they decided to do this? It's a surprisingly simple, solvent-free technique called mechanochemical ball milling. Honestly, you could just picture this as a high-tech cocktail shaker, but for atoms. It's that straightforward. You take your base QBTC powder, you toss in the salt of a second metal, let's say nickel, and you put the whole mix in a steel jar with these heavy steel balls. Then you just shake it like crazy. Well, you mill it for just 10 to 40 minutes. The force from those balls literally smashes and fuses the new metal right into the crystal structure. Boom. You've got a brand new dual metal MOF. It's super fast, super efficient, and you don't have to use any nasty chemical solvents. So, they had their new recipe all worked out. Now for the moment of truth. They tried adding a couple of different metals to see which one, if any, could create the ultimate super sponge. All right, so in the ring, we had two contenders, magnesium and nickel. The results for magnesium were, not so great. It actually ended up damaging the delicate crystal structure of the sponge, a total bust. But the nickel? Well, that was a completely different story. It turned out to be the absolute secret ingredient they were hoping for. And when I say it was a different story, I mean the performance boost was just dramatic. The original, plain CuBTC, it could store about 3.2% of its weight in hydrogen. Not bad. But their champion material, the one they cooked up with nickel for 30 minutes, it stored a whopping 4.2 weight percent. I mean, that is a massive jump in performance. Let's just put a single number on that. That simple, fast, mechanical shaking process boosted the hydrogen storage capacity by 31%. 31. Look, in the world of materials science, getting that kind of improvement from a process this straightforward, that is a huge, huge win. And hey, don't just take my word for it. Check out the data. This is straight from the research paper. Each of these lines is a different material. See those bottom lines? That's the original sponge, just doing its thing. But look, notice how the lines for the nickel versions are consistently higher? And that top line, way up there? Yep, that's our champion. It's in a class all by itself. Okay, so we know it works. That's clear. But why? I mean, what is it about adding a little bit of nickel that makes such a crazy difference? Well, the secret is all in the chemistry. It really boils down to two key things. First, pretty simple. Swapping some copper atoms for nickel atoms just created more active, sticky spots inside the sponge for hydrogen to grab onto, more places to park. But second, and this is probably the bigger deal, the process created a lot more of something called copper plus ions. You can think of these as supercharged versions of the regular copper ions, and they have a much, much stronger magnetic pull on hydrogen. And this change happens at the tiniest scale imaginable, when one little nickel atom, which you see here in green, takes the place of a copper atom. That single, tiny swap fundamentally changes the entire electronic vibe of the structure. It just straight up turns it into a way more powerful magnet for hydrogen. And that brings us right back to those supercharged copper ions. Let's look at the numbers. In the original material, only about 20% of the copper was in this super attractive state. But after they did the nickel trick, that number leaped to 62%. They more than tripled the amount of these hydrogen supermagnets inside the sponge. No wonder it worked so well. So, okay, a 31% improvement in a lab is really impressive. But what does this actually mean for the big picture? For the future of clean energy? Well, to use the researchers' own words, work like this, it brings us a whole lot closer to practical, scalable solutions. And that's the key word, right? Scalable. Because the method they used is so simple, so fast, and so green, it means you could potentially use it to make tons of this stuff. It could help us finally crack that critical storage bottleneck that's been holding back a hydrogen-powered future. Look, this new super sponge is a fantastic breakthrough, no question. But it also gets you thinking, doesn't it? If one simple, tiny atomic swap can improve a material this much, what other incredible materials are just waiting out there, waiting for someone to discover the right recipe? What other tiny changes could lead to the next giant leap for all of us? Thanks for diving into this with me.